Alright, so we're going to be addressing question 77, linear independence. The question, as you can see at the top of the screen, is determining whether or not the following sets of vectors are linearly independent. Now, I'm going to assume that you know the definition of linear independence, which basically means that one vector cannot be written as a combination of the other vectors. So we look at 77a, which you've got right there at the top of the screen, but just for convenience, I'm also just going to write the vectors down. So we've got a 2 minus 3, 1 minus 5, 0, 1, 2, 2, and 1 minus 2, 3, and 0. So I think I can tell you at a glance that these set of vectors are, okay, maybe not. Let me think about it for a second. If they're linearly independent, then I can't write them as a combination of one or the other. So the easiest way to do that would be to put them into a matrix, with each of the vectors has the columns. So I'm going to put this first vector, 2, 3, 1, minus 5, into a column, 2, minus 3, 1, minus 5, and do the same with the other vector, 0, 1, 2, 2, and 1, minus 2, 3, 0. Now, the thought that struck me before that was that these vectors do not make up a basis, but to avoid distracting you from what the question is actually asking, we'll just continue on with this. So the next step is to basically row reduce this bunch of vectors, and I think we can do that fairly easily, although this will admittedly take some calculation by hand, which I will admit I'm a little too lazy to do. But for the sake of demonstration, I think we can easily just move into, let's see. Okay, now what I want to do is that I want to make the first row, I want to make the top number in the first row a 1. So to do that, I will divide row 1 by 2. So that row 1 goes to half row 1, and that becomes a 1, 0, half. And then what I'm going to do is, now, just a general note when you're doing row reduction in general is that it's probably easier to do single operations and write out the new matrix every time, but since I have a severe lack of screen space, I will be a little lazy in that regard, and I will just try and do everything. Also note that it's quite easy to make mistakes, so if you don't get the same answers, or there will also be the possibility that I will also make mistakes. So from this, what I want to do is now make every other number below this one, below the pivot, 0. So to do that, I can just basically do row 2, that becomes row 2, plus 3, row 1. I'll put a start to indicate that's the new row 1. Alright, so 3 plus 3 is 0, 0, 1 is a 1, and 3 half, that will be negative half. And how nice, we've got another pivot 1 in our second row, so that makes our life a bit easier. So let me get rid of the other numbers below that first one here. So row 3 becomes row 3 minus row 1 star. So that will be 0, 2, and 3 minus half is 6 over 2 minus 1 over 2 is 5 on 2. And the lucky last, oh god, it's a 5. Row 4 becomes row 4 plus 5, row 1. So that becomes a 0, that becomes a 2, and plus 5, row 1, so that becomes a 5. So moving that on to the next page, and I'll just quickly rewrite the matrix we had before. If you haven't written it down already, 2 half minus half 5 on 2 5. Now the next step in any kind of row reduction is that you basically want to pivot another 1 in the second row. But since that's been done for us already, we can easily reduce these numbers down to 0. So to do that, what we would do is row 3 becomes row 3 minus 2 row 2. That will give us 1, 0, half Pardon me as I rewrite the whole matrix again. I will admit that doing row reduction is an extremely tedious process, and quite frankly, it's not something that anyone wants to do in an exam, but for now, we must suffer through this tedious process. 0, 5 on 2, plus 1 is 7 on 2. We'll come back to a 1 later. So 0 and 0, and I got 5 minus plus 1, that would be a 6. And I think that's pretty easy to see that our final matrix will be 1, 0, half, 0, 1, negative half, and then I can make that 0, 0, 1, and 0, 0, 0. So what we have here in the end is that we've got 3 columns that cannot be written as a multiple of other columns, as you can probably see easily now with a bit of back substitution that also simplifies down to 1, 1, 1, and then zeros everywhere else. So this essentially means that that the 3 vectors we have are not linearly independent, since we cannot write any one column as a linear combination of the other columns. So I would think that so hopefully this makes things a bit clearer in how you determine whether a set of vectors is linearly independent. So just to summarize, you put the vectors into a column, you do your row reduction, and you look to see whether you can represent one column as a linear combination of the others. So with that, thank you for watching, and hopefully this has helped you understand linear independence to a greater degree.